queue a user mode APC that said, I am, ready to take one, and before the thread returns back to user mode, it'll run this code. Now, user mode APC has a kernel part and a user mode part. This kernel mode part runs before we return back to user mode. And this is where we call exit thread in kernel. So it seems a little convoluted, but you'll see in a second why it needs to be this way.
Okay.
And the user mode part of this never runs, right? Because we run this part and this thing does the exit thread, which basically says, no, don't run me anymore. And then it queues the object for deferred dereference, right? Because you can't dereference yourself while you're still running because the memory will go out from underneath you. So it kind of swaps off, puts itself on a list, and it's asynchronously dereferenced.
Okay.
Object manager object, right? And then when the last dereference goes away, the whole thing gets deleted.
Okay.
So you're wondering, why is it this complicated? Well, it's this complicated because what if we're in kernel mode at the time you take one of these? You don't want to just blow it away right there. If we blew it away right there, let's say we are in a system call, you've allocated a bunch of memory in kernel, like non-paged memory, whatever, and we blew you away right there, all that stuff would be leaked, right? And that's like a serious problem because kernel resources are shared amongst everyone on the system.
Sure.
So if you could just create a whole bunch of threads and blow them away when they're in the kernel and leak a whole bunch of state, the machine would be unusable, right?
Yeah.
So what we want to do is we want to queue a kernel mode APC. The kernel mode APC will only fire when we're running at less than APC level, effectively, in kernel. We do some tricks where we have these things called critical regions, but conceptually, when we're less than APC level in kernel, this thing will fire, right? And what it does is basically queue this user mode APC so that right about when we fully unwound our stack from your call into the kernel, it will fire, right? Because right when we're about to come back to user mode, it'll run this part of it, right? Mm-hmm. So the kernel mode APC is just required in order to queue this thing in and kick you out of a wait, because you could actually be in the kernel doing like an NT, or at the Win32 level, wait for single object. Right? You could be waiting on an event, so effectively you are in the kernel. So the side effect of queuing the kernel APC is that it'll kick you out of this wait and abort the wait.
Okay.
So you'll start unwinding, right? Because at some point you're in the kernel in this, NT wait for single object, KE, whatever, wait for object. And what happens is it will get aborted and start unwinding. And right when it's about to come back to user mode, you take this last thing in it, and then you get blown away. Okay. So you don't leak any state that might be intermediately on your stack, like a temporary allocation or whatever it is, right?
And the same is true for wait for any, right?
Yes.
So just any of those waits.
Yeah, if you're doing like a user mode wait, you can get kicked out like this.
Okay.
Right. So the idea is there are certain cases where we've taken a kernel lock, right, and we're manipulating some kernel structure. So what we do is we basically block the kernel APCs before we take the lock, so that once we're in the lock or waiting on the lock, we don't get aborted from that wait.
Okay.
Now it's a little complicated, but maybe if you sit back and think about it a little bit, you'll see why we kind of need to do all this juggling.
Absolutely.
Yeah.
Because you don't want to leave any corrupt state in the kernel and the story.
Right, but then a side effect of this is that anytime we're going to take a kernel lock, we first need to raise to APC level, effectively. Right, so we can block both these terminate APCs, and suspend is also implemented to the kernel APC. So there's a whole bunch of aspects here, but fundamentally the key is it needs to be done at this point so that we've unwound the kernel stack.
Absolutely.
And we freed everything up. Now the difference with kernel threads, system threads, is that there is no user mode. They never return to user mode. So how does this work? Well, you can't terminate a system thread from a different thread. It basically has to terminate itself when it's done. That's basically the design there.
Okay. Which makes sense.
Yeah.
That's good. I mean, it's good for stability and reliability of the system.
Yep.
I mean, very cool. Well, learned a lot here.
Yeah.
I mean, there's a lot goes on. I mean, it's good to talk about because there's so many issues with threading, right? Threading is one of the big burdens for programmers, especially dealing with asynchronous threads
Right.
and the whole parallelism, parallelized code, and it's just hard to write concurrent code, et cetera, et cetera. So really digging into what a thread is was, I think, was very useful today,
Sure.
and how they work on the system. Is excellent. And some of the changes he made in Vista, which the process that doesn't require any threads is interesting,
Yeah.
or the one that gives you a default execution context that you can't inject or suck out of,
Right.
which is interesting.
So that was one of the new things. We did other things like you improved the quota management, so you could say this user can only have this much working set or this much non-page pool or page pool or this kind of stuff. That's more for the government security regulations. Also, this thing can't use this much more than CPU, right? You as a user can't use more than 10% of the CPU. That's enforced now. We've
Okay.
done that. Create processes user, we moved that into kernel as part of all this stuff so that you can basically inherit handles from your parent when you create a process as a different user that didn't used to work in older releases. So things like this, incremental improvements, big underlying architectural changes. So
Sure. All in the name of security, stability, and reliability, which is very important,
yeah,
right?
Yeah.
And performance.
sure,
I mean, there's going to be implications on performance here.
right.
So let's talk quickly. How long have you been working at Microsoft? Like, how long have you been working on this stuff?
So I've been at Microsoft for about 4 years.
Okay.
This specific stuff I've been working on for about the last 2 or so.
Okay.
But I've been working in the kernel for about 4 years here.
Cool.
So
And what attracted you to kernel development?
I really like the low-level systems problems and the kind of stuff we have to think about here, the kind of synchronization, all these kind of issues of what code can run on top of what code, and kind of this whole mindset of once you go into the kernel, everything that as a user at a user level we think of applications, whatever. Going into kernel, it's all data structures, right? You can manipulate these things, like work out how these things work, and building the platform, really, right? Platform on which you can do all this stuff. So I was into that always, so it seemed like a good place for me.
Good. Well, great job, man.
Yeah.
Looking forward to seeing how this manifests itself in Vista. I'm sure it'll be sort of light manifestation for those of us who spend much time in user mode.
Yeah.
But I still, it's cool that we talked about the complexity of terminating a thread and what happens. Because as a programmer, you just call APIs.
Right, and I think it was good that you touched on this fact that you can't really do it unless you
know what you're doing.
Now, the difference with terminate process is none of the threads are going to be running, right, anymore. So that's okay, right? When you blow away a process, we just incrementally terminate all of them and block creation of new threads in the process. Now, that's okay because all of them are going away. You're not going to be in a state where you're hung or whatever, right?
Mm-hmm. Well, I mean, this explains perhaps why. Well, it does explain. So sometimes when you go into Task Manager and kill an application, it doesn't kill right away. Is that because of the cleanup that you're doing? So if I kill a process in Task Manager, say it's...
So, as I said, if the thing is waiting in kernel, right, it doesn't take necessarily that thing to back out, right?
Yeah.
It's only if it's doing a user mode wait, right? And the process doesn't actually go away until all the threads have died from Task Manager. So even though you'll see this kind of ghost laying around maybe in Task Manager until all of them have run through this code path, right? And when the last thread goes away, we go into what's called process rundown, which is where we, close all the handles in the process and delete the virtual address space, most of it. And then finally, the process object itself finally goes away when the last reference to it goes away. But effectively, it's dead when the last thread exits. It's different than object delete. It's kind of an important distinction.
True. Well, a thread isn't an object, right? Or is it?
Well, they are. Like when you do a create thread, you'll get back a handle. It's an object manager object. The e-thread is an object manager object.
Got it.
Right. Yep. So the process handle is a handle for the process. So once the process has died, right, you can't create threads in it anymore, even though you still have a handle, right? So the process object still exists, so you can query some information about it. The ID remains, right?
Sure.
The ID only gets recycled when we finally delete the object.
Okay.
So stuff like this, right? There's a slight decoupling between the point at which the process dies and the point at which the object is no longer valid.
And so if I tried to create a thread in a process that's in the stage of dying,
It's not allowed.
It would throw an exception.
No, it just fails.
Just doesn't
It
work.
just
Get
says
an
process
E.
is terminating error.
Got it. Very cool. All right. Well, thank you for your time.
Sure.
been
Hopefully
good.
this was educational.
It definitely was, and it's always fun to talk about threads and processes and whatnot, and really dig into how the system's working. I think
Okay.
it's important to get an idea and to meet the people who are making it happen. That's also number one. All right.
Thanks.
Thank you.